Hi, welcome to the video, and thanks for taking part in this study. In this video presentation, we'll be looking at the different kinds of vector products and the way we use them in mechanics. First, we'll do a review of vector components, then we'll look at the inner or dot product, the outer or angle product, and then the vector or cross product. And we'll do some examples of work and angular momentum and torque. Let's start with a quick review of vector components. Any vector can be written as the sum of components. They can be the x, y, z components. For instance, we have a vector r here, which goes from the origin to the far corner of this imaginary rectangular box. And the components, rx, ry, and rz, are the projections of r on the I, j, and k axes. A vector's components can be parallel or perpendicular to another vector. We can decompose a vector into parallel and perpendicular components. We have here a force acting on an object that is moving with velocity v. We remember from geometry that two vectors define a plane. And in this plane, we have one component, f, that's parallel to v, and a component of f that's perpendicular to v. The parallel component of f changes the speed or magnitude of v, and the perpendicular component of f changes the direction of v. Now let's look at our first product, the inner or dot product. Here we have two vectors, a and b, in the xy plane. The inner product is the product of the projections of a and b on the x-axis plus the product of the projections of a and b on the y-axis. So that's the sum of the products of the projections. The other way to define the inner product is by projecting one of the vectors onto the other. Here we have a times the projection of b, or b cosine theta, or we could have b times the projection of a, which is a cosine theta. The inner product is a scalar, so a dot b is going to be equal to b dot a. Let's look at an example using the inner product. Here we have a mover pushing a crate up a ramp. The crate is moving in the direction d. Now the crate's kind of short, so our mover has to push down a little bit in this direction, f. Work is the inner product of a force and displacement. So the work, w, is f dot d. In this case, we'll use the parallel component of f with d and get df cosine theta. We could use Cartesian components. We could say f dot d is fx dx plus fy dy. In this case, we've chosen our coordinates so that our y-axis is vertical and our x is horizontal. But we don't have to choose that. We could actually choose more convenient coordinates so that our d is in the x direction, in which case f just has an x component and a y component. So our work is f dot d, or fx times d, or again df cosine theta. Our next product is the outer or angle product. The outer product of two vectors is a rotor. Instead of a direction, a rotor has a sense, either counterclockwise, positive direction, or clockwise in the negative direction in the plane of the vectors. If you think of a vector as a directed line, you can think of a rotor as a directed area or a directed arc. So instead of an arrow above the vector, we have an arc above the rotor. The direction is defined by starting along A and then turning along B. So that gives us a left turn or counterclockwise. Or for B angle A, we go along B and turn towards A for a clockwise C. The magnitude of the outer product is the area of the parallelogram made by the vectors. The area is the base, A, times the height, b sine theta. Let's look at torque. Torque is the outer product of an applied force and the radius from the point of rotation to the point where it's applied. The sense of the rotor, tau, here is counterclockwise. We go along r, turn left, and that gives us the direction of tau. The magnitude is the area of the parallelogram formed by r and f. The units of torque are Newton meters per radian though we usually just give this as Newton meters. So the magnitude is RF sine theta. Now the work done by torque is the applied torque times the angular displacement theta. Work does have units of Newton meters because theta, of course, has the units of radians. So we have Newton meters or joules, and our work is just equal to tau times theta. We just saw the rotors for torque and angular displacement. So other rotors we should know are the orientation of an object in space, that is roll, pitch, and yaw angles. The angular velocity is omega equals d theta dt. Angular acceleration is just d omega dt. And our two different kinds of angular momentum, we have our body or rotational angular momentum, which is just our moment of inertia times our angular velocity, or our orbital angular momentum, which is our radial vector angled with our linear momentum. The outer product of two unit vectors is a unit rotor. Each unit rotor has a dual unit vector. So we use the circle symbol for unit rotors just like we use the hat symbol for unit vectors. So we have unit vector I, angle J is unit rotor K. And then the dual of the rotor is perpendicular to the rotor, completing a right-handed space. So if we curl our fingers around in the direction of rotor K, our thumb will go up in the direction of unit vector K, completing a three-dimensional right-handed space. Now the outer product of J and K is the unit rotor I, and Ki is the unit rotor J. Now we can add rotor components together just like a vector. So for instance, our orientation is the sum of our roll, our pitch, and our yaw around our I, J, and K rotors. Now here's an example of using rotors, angular momentum, where we're going to add two rotors together. So the total angular momentum is the rotational angular momentum, I times omega, and the orbital angular momentum, which is the outer product of our radius and our linear momentum, or r angle mv. The third vector product we're going to look at is the vector cross product. The cross product of two vectors, a cross b, is a vector perpendicular to the two being multiplied. The right-hand rule determines the positive direction. So if we put our index finger along A and our middle finger along B, then our thumb points the direction of A cross B. And like the outer product, reversing the order reverses the sign. A cross B is equal to negative B cross A. The cross product is an axial vector, and an axial vector determines the axis of rotation. So the direction of vector tau is perpendicular to R and F and out of the screen. That is, if we put our index finger along R and our middle finger along F, our right thumb will be along tau coming out of the screen. The cross product is the dual of the outer product, and so it has the same magnitude as the outer product. That is, tau is equal to RF sine theta. With torque, just like with torque, we can use the cross product in place of the outer product to describe the angular momentum, since the magnitude is identical. Here, the direction of omega is along the axis of rotation, and the direction of the orbital angular momentum is defined by the right-hand rule. R cross mv gives this direction. For each rotor, there is an axial vector that is the dual of it. We've seen torque in both rotor and vector representations, as well as angular momentum. Other rotor axial vector pairs are angular velocity. Rotor omega is the time derivative of the angular displacement, whereas the vector omega is d theta dt in the direction of the angular velocity determined by the right-hand rule. The angular acceleration in both cases is just d omega dt, and as we saw, the angular momentum is I omega and r angle p, or r cross p. Thanks for watching this presentation, and thanks again for participating in our study. We'll be seeing you at the tutorial session. Goodbye.